overcome the phobia significantly. Not absolutely, but we can improve it a lot. Okay? Like the snake, if it is one, perhaps, yeah, it's fine, let it go. There are multiple, maybe a little bit scared. But how we will be able to do that? We don't want to bring the snakes here. Okay? And we don't want to put the participant in the real threat. Okay? So we need to find a way so that we can introduce that and try to overcome the phobia or disorder. Okay? Now, exactly the project I'm talking about is biofeedback driven self-guided virtual reality exposure therapy. So basically, this is a virtual reality that we're going to create to introduce the exposure therapy. And here, a couple of keywords are related, like the biofeedback driven. That means we want to provide the biofeedback in real time, and that feedback will be provided based on some physiological symptoms or signals that we can count. Okay. David mentioned that a big name here. Yes, that is meant to be here because we are very open and very collaborative. So I'm going to name them individually so that I can inspire you all. Yes, we have the chance to do the collaboration, and it's a very much multidisciplinary project. Okay? It's actually kind of eye-opening, like how the multiple discipline can work together to achieve a specific target. Okay? Here myself, David Brown, he's the person who actually introduced me in this virtual reality exposure therapy with his fantastic paper. Okay, when I stepped in his lab, the first paper I came across, it was the virtual reality exposure therapy. So he's kind of guru of mine. Now, not to mention this name, you already have seen this name, Matthew Harris, excellent PhD student from our department, working really hard to give a real shape of many of the projects. And after that, we have the Nicholas Shopland, who is always sitting behind doing the most techy stuff. Okay? These two names are very interesting, Nadia Haim and Alexander Shumich. They are psychologists. Okay, now see, so far we were talking about only computer science, but the psychologists are coming, because whenever we are talking about arousal, phobia, disorder, we are not expert of that. Okay, we can play with machine learning, we can play with the data, but we can't actually say anything about those kind of things. Okay, we need someone who can really make a meaningful comment about that. Okay, then we have some students again, Ruth Amy, who is going to present a paper in 2 days. And here Jackie is a PhD student, Brad is a PhD student, David Downes is another David. He's from architecture department. Now see, computer science, psychology, now architecture. Because whenever we're talking about virtual reality, architecture gonna play the role. The lights is nice here, but who is designing the light? Okay, the architect. Okay, they are giving us the ideas. Okay, so then we have Yangan and Shane, Preeti, who is also very one of the key person of this virtual reality exposure therapy, and then Andrew Burton and James Lewis is also there. So just to give you the idea, this is one of the projects where multiple people are working together to achieve a same goal. Here we are coming from diverse background, but yet to tackle a common problem, we can work together. We have to think where our expertise basically lies. Okay? So though it's a specific project, but this slide is very much meaningful, how we can be assistive or collaborative with one to another. Okay, so we have this bit of collaboration. Now, machine learning pipeline for stress detection. As you know that whenever we are seeing this kind of thing, like a snake or going to on top of the skyscraper, we can be really afraid. But that relates with some physiological symptoms or changes as well, like our heartbeat can increase. Okay, or we can sweat. Okay, now if we can bring out this kind of physiological change, perhaps we can identify whether we are stressed or not. Okay, so initially we thought, okay, let's try to figure out some of the data which could be multimodal. Okay, multimodal in terms of let's say heart rate or EEG signal or EDI. I mean, sorry, the sweat, skin sweat, or many more other things. So we can calculate, collect those data. And as you know, machine learning model always collect the data, do some feature selection, model trains, automated machine learning. We used at the beginning, it was bringing up all the known machine learning model to give a parameterized optimization, and we can think about a model to find which can be related to stress detection, and that stress could be many more places. Like yesterday, I was talking with some people here, and they were saying we are very stressed when we are working because something is not going right. This mail is coming, that is complaining. Yes, we can be stressed, but that is very logical, and that can impact our work quality. Okay, so that can be related here as well. Or David and we are all working toward the special students with autism and other. We are talking about meltdown detection, and so that can be related as well. Or any other application domain that's related with that. Okay, so now we are seeing this machine learning is coming to stress detection, and now here, what we are thinking, the machine learning models can be helpful in the real-time VRET, or the virtual reality exposure therapy. Now, as we said that if we can provide the virtual reality exposure therapy and the feedback in real time, that will be really amazing to see how the participants are doing. Now here, we have to take a use case, because when we are thinking about virtual reality, it's not that easy to create a virtual reality. Okay, it's quite challenging. So for this particular project, what we did public speaking anxiety or disorder. Like sometimes we're very afraid when we're talking in front of other people. Mostly students, they're nervous when they're presenting something. Even some of us in early stage of our teaching career, perhaps we were nervous, isn't it? So we took one of those cases, like the public speaking disorder or public speaking anxiety. And that anxiety, we wanted to pick it up when we are anxious. If we are anxious, we can say, okay, the participant is anxious, let him cool down, let him settle a bit, and then allow him to talk again. And over the time, if we can do that, that person will overcome the fear, the phobia, the disorder that we are talking about. Now here, this is a nice pipeline, I will say. Let's say here we are collecting that data, feeding it to the machine learning model, and that machine learning model basically identifying our stress level, okay, and showing in the real time how, I'm showing you, I'm going to give you an example in a minute, all right? And that can be used in multiple participants, because if we can develop the framework, that framework can be used for multiple participants. And that multiple participant basically helping us to train our model even further. Okay, like it's a real-time model we are talking about, but well, technically it's not absolutely real. We need to give a little bit of time to do the shortest possible computation even. So we need a little bit of constant delay, let's say 5 seconds or so, because whenever we are collecting the data, we have to give a calculation time. Okay, so if you want to feed it back based on the calculation, it's not going to happen in 0 time. Okay, so we can think about, okay, we're going to wait a couple of seconds or 5 seconds, and after 5 seconds, there will be a constant feedback. Okay, so here, this feedback is helping to the participant in the real time to tell their level of stress, level of arousal. Okay, now here is an example. It is a combination of multiple things. The first thing, we have to think about the peripherals, like what type of data we are going to use. So we used a BCI, brain-computer interface, all right? So it is a EmotiFlex with 32 channel. Okay, so we were collecting that data with the 32 channel EmotiFlex, as you can see. So this is something to collect the data acquisition, and on top of that, what we used VR headsets. So Nick, Matt, and others actually in our team, David Downes, they create a wonderful virtual reality environment with the setup of a lecture theater, where actually you can change the situation from participants, colors, lights, and their activity, and so on. Because sometimes, like Ree is moving now, it can make me stress, all right? So she is leaving. But sometimes it may not. All right, now how we can identify that? We can regulate that. Okay, so, okay, everyone is very silent. Okay, fine, that is one kind of thing. But some other people are not very focused, doing some unknown activity that I'm not expecting. So that can also make me stress. So we can change those scenario or setup. Actually, thanks goes to Nick again, because they were working really hard to change those kind of change in the virtual environment. And at the same time, what we were doing, we were collecting the brain signal with the emotive flex. And when we're talking about the emotive flex, in the headset, we are seeing this kind of virtual environment, that is a classroom setup, all right? So that can be changed based on the different setup. So this is just a snapshot of the real virtual environment, okay? But if you are looking around, up and down, it will change. So it's just a 2D representation of a 3D constant one. Now, there are some interesting bit as well. Perhaps you can notice that some heart shape, all right, or some brain shape, they are basically the indicator, okay? So they can be changed. I'm going to come to this slide again. Now, to change that, as we can see that we are using emotive flex with 32 channel, they have, it is their I20 representation, like particularly which part of our brain is more active, or actually which part of the brain might be related with the anxiety. So we need some experts from that domain, and they were telling us, okay, I want to particularly focus on that part of the brain, or this side, or this channel could be much more interesting, and we were aligning at that, based on that level. And as we are talking about, it's a real-time one. Now we need to think about, whenever I'm talking, I'm also getting a sense actually how I'm doing. So what we did, we thought about a windowing approach, a sliding window. Like every 5 seconds, we're gonna move forward. We're gonna collect the data, chop it down, throw it in a place for 5 seconds worth of data, and we're gonna calculate what's happening between and generate some feedback for that. And by the time I'm calculating, the data is generating, because it's a real-time one. It's producing some feedback. In the next 5 seconds, it's coming the data again. Now I need to do the calculation again based on the new activity. Okay? So that's how we moved forward. And these activities, the calculated result, actually related with our arousal. Okay, now we can see that if we are going through the spectrum of the brain signal, there are already, it's reported, like if we are doing some stressful work, let's say mathematics, all right, which takes a clear utilization of our brain. So we can clearly see that yes, before and after, the signals are very different. That it's a clear indication that the brain is actually helping us to get some idea from that. Or if we are thinking about, that is another one. Again, before a stress level or after, we can see how this time frequency representation can change. So we can try to pick this bit of change based on our specific area that actually the experts suggested. Like yes, for this part of the activity, this is the brain region, they are more active, try to identify those areas. If they are behaving unexpectedly, pick it up. Okay, and try to give some feedback at that time. Okay, right, so now here, also some other things can be done. This is an interesting task I found, because it was done with the research group, but Professor Alex Shomik, who is an expert in this brain signal data analysis, and also Mufti, they work really hard in this domain. Alex was on the on the belief like, yes, we can collect the heart rate from our brain signal as well. He was believing that theoretically, okay, but we didn't have any clear proof that time, like how we can do that. But he had some idea, okay, this part and that part we can place them to probe in bipolar orientation, and we can do some particular order of frequency analysis, signal analysis, and then we can perhaps be able to collect the heart rate. And we went through a series of experiments to analyze that with two particular probes in a bipolar orientation. And after a good amount of research, we found, yes, something is appearing. And we found the spikes looking, these are the heart rate. Okay, now we can see that the heart rate, it's coming. However, some of them are doesn't related with the actual heart rate pattern. That means some of them might be informative, but some of them are misleading. Now we need to find out which one is misleading. So we had to find out the misleading one. There were some tools to, thankfully, and we found that we used the tools to clear those out. And we found, yes, these are the peaks that can be related with the heart rate. And it was really interesting that when we are calculating the heart rate from the brain signal, it is actually matching with our heart rate from the watch as well. And it was really interesting. Okay, because behind the scene, we were trying to minimize the peripherals, because you may say, okay, heart can be calculated from the watch. Well, I'm gonna do so problematic thing. But keep it in mind, we are trying to minimize the number of peripherals that we are using. Okay, that is one of our interests as well. Now, from there we have calculated the heart rate, and that heart rate was basically related with these heart shape. You can see this one is, anyone, female person can tell me the variation. This is pink, right? Close to pink, because I'm not that much aware about the diverse range of the colors. But this is red. That means if the heart rate grows, we can change its color and shape as well, and size as well. Okay? And some other brain function activity as well. Then we can see this one is a bit bigger in the size of brain, and this one is smaller. That means it actually identifying different brain activity. All right? So this is actually helping in the real time, not at 5 seconds delay, to provide the biofeedback. Okay? Last, this is one of the work that we have done. Now, just to add a little bit, Ruth, that I mentioned earlier, Ruth Amy, she's a master student of mine. She is working with a different modality now. Okay? Now, we are talking when we're giving speech. Like, this can be an indicator for our anxiety as well. Okay? Now, if I'm anxious or disturbed or not feeling comfortable, that can be identified through our speech as well. She's working with that, and she's working, if we can identify it through our speech, because we are talking about public speaking disorder, that means we are constantly talking, all right? That can be an indicator for our anxiety level findings, and other people, as we said that, and she has achieved to reach 97%, 97.5% of accuracy with a recall of 98% with the publicly available data set. Because in our experimental setup, we have collected, we haven't collected the speech, but we have collected only the brain signal. But we can easily store the data and utilize this data for the feedback as well. So this is an ongoing work. We are working in this line. And maybe we're going to introduce in our real experiment where Nadia and Alex are experimenting with the students. Yeah, that's it. Thank you very much.
Any questions for Arif? How you might see that being used in higher education? A lot of our students in our first year have to give their first public speeches at most of them, some of them are completely terrifying. So once we prove the efficacy of this approach, we're going to introduce it. Other people in Nottinghamshire, where we come from, are very interested in using this in schools as well. Or if you're a person with autism who has some apprehension about social situations as well, you can have great, we have an ex-student of mine who is a person who stutters, with stutter. And he sort of devised a series of virtual environments, a job interview, going out with friends, a social situation where he gets people to enter situations, people who stutter, and are forced to carry out conversations in a graduated way. There are many ways you can use virtual reality exposure therapy, as well as producing things like virtual labs as well. So I think that's one of the interactive, immersive opportunities we have for the future of higher education. So, the last speaker of the session is Professor Mufti Mahmood. And he, Mufti is going to be talking about his work in early detection of Alzheimer's, using his brain signal work and data science work. So, Mufti, I know that thought that might be him coming to the door.
I hope he's not attending.
Thank you very much. Well, actually, I had the plans to talk without any slides, but having seen that how professional David and Arif had been, I was forced to prepare some slides, okay? So it is not preparing the slides from the scratch, but some of them I'm reusing from some of the existing work that we have been doing with a number of different Bangladeshi organizations as well. So, well, this is something a little bit different from what we have been hearing in this workshop. We are talking about inclusive education, but now in this talk I'm going to talk about a little bit about inclusive society, because you know that we all agree that given the technological advancements that we have in the recent years, our life expectancy is going high, yeah? So people are living many more years thanks to the technological innovation in med tech, okay, medical technologies as well, and the different diagnostic techniques that we have right now. Therefore, well, how can we actually increase or improve the quality of life of people? Now, what do I mean by quality of life? Of course, this is something which does not only involve the elderly people, it also very well involves the quality of life of students who are with disability, who are in the verge of, let's say, exclusion in terms of their participation in the society. So right in this presentation, brief presentation, what I'm going to focus is that, well, how can we actually support the people who are having some issues related to their age, okay? All right, so seeing this photo is very, very close to my heart because, well, we are probably standing somewhere here, okay? Some of us, okay? Many of you are probably still in the green zone, okay? So we are already, yeah, we are already in the amber zone, going towards the red zone. So this is something which actually all started after a very close discussion with Professor Shamim Kaisar, well, who has been a very close friend for a very long time, and we do share a set of common goals that, well, how can we eventually improve the quality of life of people here in Bangladesh as well. Therefore, as you can see that, well, over time, we all are losing our capacity, mental capacity, okay? So, for example, let's say that when we are young, we tend to be very energetic, remember many things, but as we progress over the years, we tend to lose our mental, let's say, the brain cells, okay, which are the neurons, and then eventually there are a number of different conditions that we are struck on. So this is something which represents the patients with Alzheimer's disease, okay? So as you can see that right now, the projection is that by 2050, there will be around 106 million Alzheimer's patients worldwide, so which is actually a very large number. Now, if we think of the non-communicable diseases, where which is very common around the world. So we know that cardiovascular diseases is one of the main killers. Then we have the cancers, chronic respiratory diseases, diabetes. But many of the people do not talk about is the neurological disorders. Okay, so there is a large number of neurological disorders that actually impact our ability to be included or contributing in the society. Because, well, neurological disorder does not kill us immediately, but what it does is it makes us incapable to be contributing to the society. Okay, it enforces us to take a life which is lower in quality, dependent on a number of different technologies and also caregivers. Okay, for example, if someone is having a heart attack, well, people will have heart attack and die here. But think of someone who is having dementia. Their life is much more miserable than someone is having a heart attack. Okay, because when they are there, they are putting a lot of burden on the society, on the family members, and of course, well, they themselves are going through a situation which is really, really very difficult to cope. Right. So here, if we see the statistics, well, it is a lot of things which are impacting our quality of life, and in all those specific aspects, AI actually can play an important role. And it is not only AI; it is the explainable AI that we are interested in. Okay. Now, with all the populations, what we want to eventually try to address is that, well, how can we actually improve certain things in the lifestyle and improve the people's situation in the neurodegenerative diseases. Now, all these things are combined together under the umbrella of electronic healthcare. Okay, so e-healthcare, and we know that there are lots of different type of data that can be collected thanks to the advancement in the diagnostic technologies. Okay, and the data acquisition techniques. So we want to improve the healthcare delivery and planning, especially let's say that within the context of societies or countries like Bangladesh, the low middle income countries. This is something which is very, very important. And what we want to focus is actually a patient-centric approach. Okay, so it is something which is not the doctor or clinician-centric approach, but a patient-centric approach where we would like to, let's say, develop tools which are going to be useful for the patients. And the electronic healthcare is defined by the World Health Organization as the combined use of electronic communication and information technology within the healthcare sector. So given that we all have access to the digital technologies these days, thanks to the, let's say, thanks to the development in the internet technologies and the communication technologies, we all can have real-time data, patient data, and that is something which can be then included or added or integrated with the electronic health record data that are available with the healthcare service providers. Right. Now this is something, as you can see, and we all agree that the data, the volume of data is exploding. A lot of data are being collected over the years, and this is something which is only increasing every single day. And the data sources mainly within the healthcare pertains to the diagnostic imaging, electrocardiogram signals, and then genetic diagnosis, data coming from clinical laboratories, then data coming from mass screening, and a number of different other sources, for example, wearable and all these things. So a lot of data are currently being collected. And well, these are some of the existing tools which are out there, different devices that are facilitating the data collection in terms of, let's say, electronic health records, test results, the imaging data, and all these things, okay? Now, we have applied a lot of deep learning techniques, okay? So the AI models became very prominent in the recent years, in the last couple of decades, thanks to the, let's say, development or let's say, reinvention of the deep learning methods, because deep learning was there from long time ago. But what we didn't have was the machines that can run or execute these models. Once we had those, let's say, devices that can run or execute these models, we could apply them on a number of different models, okay? So there are a number of different models that have been used in the literature, and predominantly CNN, then fully connected networks, then deep autoencoder, and a number of different models have been very widely used within the healthcare domain. And well, we along with Professor Shamim Kassar, we did a work on identifying what are those popular models and then how do they contribute. And then eventually the goal was actually how to, let's say that, employ the different types of data, because you have seen that there are a number of different data types which are available to combine and deliver something which can extract insight from each of these data types and then provide, let's say, actionable insights from those data. Now, this is something which would facilitate the data-driven decision making in terms of the diagnostics, preventive medication, precision medicine, the reduction of adverse medication, cost reduction, and improving overall the population health. So there are a number of different positive aspects that we can gain in from here. As we mentioned that with Professor Shamim Kassar, well, there are a number of things that we did in terms of AI's application to the biological data, deep learning's application to mining biological data, a number of different application domains. But what is interesting is that how can we make these tools that are available to be adapted within the practice. Okay, one of the main barriers, because well, David, Arif, Shamim, myself, we all are actually working very closely with the stakeholders. For example, like doctors within this particular context. Whenever we bring a particular model to the doctors, they say that, well, tell me how your model is deciding that this is this disease. Now, let's say that, well, empirically we understand that how this training process is happening, but what are the relevant factors that are contributing to the decision-making process, okay? Given that most of the deep learning models are very complex mathematical models, and because there are the forward propagation and back propagation of the weights, most of the times we cannot really keep track of how these models are actually implying or extracting the relevant parameters that can lead into the actual decision-making process. Therefore, the increasing, let's say, demand from the physicians, the clinicians, of that we need to have a better understanding of how the models are deciding what they are deciding, okay, what they are suggesting in terms of the classification. We had to move from the black box AI to white box AI. And within that particular context, well, we have done a number of work, okay? For example, trying to identify that what are the specific models which are out there through certain systematic reviews, and then also within the context of the Alzheimer's disease, try to understand that what are those local, global, and then post hoc, ante hoc models are available for the explanation of Alzheimer's disease detection, and of course also certain usage of explainers, explainable methods like LIME and SHAP, how they have been used within the context of Alzheimer's disease detection. And all these things centered onto certain central research questions. So that is what we wanted to understand through these works. So here, that can we actually have some intelligent and cognitive systems for detecting the conditions that actually reduce the quality of life, okay? So this is something, for example, if someone is having that Alzheimer's disease, can we actually detect it early on, okay? And how the different data modalities, for example, as you have seen that there are images, then there are, let's say, electronic health records, there are wearable sensor data that we all are collecting, how these individual modalities are contributing to the detection process. And do systems integration of multiple data modalities improve the detection process? So whenever we are bringing these different type of data together, are we actually improving the process of the detection? And can these methods justify or explain their decision-making process? So, well, we are adding one modality after the other, but how it is actually improving the decision-making process? And most importantly, in the recent days, and which is the upcoming research arena, I think, okay, and where a lot of you can contribute as well, is that, well, we have one modality of data. For example, we have brain imaging. Can we infer from the brain imaging other modalities of data? For example, like the EEG data. Now, why is this important? We recognize that, well, multimodality plays an important role in the detection process, okay? So if you have imaging data, you add EEG data to it, we can identify the diseases better and quicker. But not everywhere, all the facilities would have all the apparatus or the devices. So if one facility, one healthcare service provider has got one modality, can we automatically actually infer the other modality? Now, of course, well, we understand that generative AI has got a number of different aspects or risks, okay? But these are the applications where we can actually use generative AI in a very productive and an impactful way, right? So within this particular context and involving the Bangladeshi population, one of the main focus of us has been the Alzheimer's disease detection and dementia. We are working very closely with the NINS, which is the National Institute of Neurosciences, okay, here, and Professor Din Mohammed. With Professor Din Mohammed, we actually had conducted a couple of workshops. One of these workshops took place here in this very room, actually, one and a half years ago, okay? So we conducted where we brought different stakeholders, doctors, software engineers, patient groups. We brought these people and we sat with them that what is the system requirement, okay? And then how can we develop systems that are going to be useful for Bangladesh? The similar kind of workshops we conducted also in India. Because our goal is that all these plethora of different methodologies which are out there, how can we adapt or improve these methodologies for the population here? Because you see that, well, one of the main challenges of AI models are, many of the AI models are pre-trained, okay? And majority of the pre-trained models are trained on a different population, not on our population.
Let's say Western Europe.
So,
Let's say Western Europe.
So on a different population, okay? I don't want to be very particular, okay? So because they are trained on different populations, therefore what we need is, we need models and data that can be utilized for our population. Therefore, we have been working on developing a data collection system, and well, we had an agreement with NINS, okay, National Institute of Neurosciences, that they would roll out some of the technologies or these data collection methodology that we have developed. But in between, as you all are aware, things have changed since last 1 year, okay? So right now the things have slowed down a little bit, but we hope that we'll be able to pick up on the things that we had been doing. So within this particular context, there are a number of different challenges where I think that all of you can contribute, if not all, many of you. For example, cross-modal data generation, the thing that I was saying, that we have one modality of data, can we actually infer another modality of data from there? For example, we have electronic health record based on and neuroimaging. Using these two, can we identify what are the EEG patterns of all those patients? Or we have, let's say, certain fields of the electronic health record. Can we actually infer the other fields of the electronic health record which might be relevant for Alzheimer's disease? As David was mentioning, as a part of the Phase 4 AI project, well, where synthetic data generation is an important aspect, but within the context of synthetic data generation, can we actually generate cross-modal data within that particular context as well? And of course, automated annotation of different brain regions. This is something which is really, really important. Well, because when we are generating synthetic data, whether these synthetic data are relevant to the original data or not, okay? So that is something where there is a lot of space a lot of place to contribute, a lot of opportunities to contribute, and not to mention explainability. Our understanding about these AI models are still at the very basic level. Whenever we are talking about explainability, most of the times we talk about post-hoc, which means that, well, the model is delivering us something. Now we are going back and trying to understand that how this model is making sense. Rather than, the better approach would be that the model itself would tell you while it is making some decisions that how those decisions are being made. So inherently explainable methods is something which a lot of research opportunities exist, okay? with this, I would like to thank you again for your patience. And well, this is something where we are not the one who are contributing. So there are lots of people altogether that are contributing to this cause. And I really welcome, that well, more and more people should come on board and contribute to this cause. Okay. With this, I would like to thank you very much for your attention. Please feel free to get in touch in the future if you would like to contribute to this. Thank you. Any questions?
Well, since Mufti said he hadn't prepared any slides, going from that to that, that's amazing. Thank you. So we have some guests to welcome now, Mufti.
Thanks.
Okay, everybody, so we have a quick coffee break now.
Yes.
So, quick coffee break, but we are then going to start at 3:30 because we have a very honourable guest from University Grants Commission and from the British Council here, so we are going to stick to schedule. So quick coffee break and then back in, please.